Okay, so what I want to do now is to look at non-homogeneous linear differential equations. So in particular, I want to look at the following. I want to look at ay double prime plus by prime plus cy is equal to a function f of t. And I don't want it to be homogeneous, so I don't want this to be the zero function. So not zero function. Okay, and again, a and b, c are constants, real numbers, and I'm going to assume a is non-zero to make it a second order differential equation. Okay, so I want to come up with a general solution to this. And we've come up with a general solution to the homogeneous situation, but I want to try to work out what happens in the non-homogeneous case. So let's fix for a moment ypt, a particular solution. So what does this imply? Well, i.e. ayp double prime plus byp prime plus cyp is equal to f of t. Okay, so I've fixed a particular solution. I don't know how I've found it at the moment, but just assume we have one. Let y of t be another solution. So I've got a fixed one, then I choose some other one. They could be the same, but let's just choose another one. Be another solution. Okay, so what does this imply? Well, this tells me that ay double prime plus by prime plus cy is also equal to f of t, which of course is equal to this. Whoa. So what can I do? Well, I can take the difference between these two sides and I'm going to get 0. So this implies that if I simplify things after taking the difference, a times y minus yp double prime plus b times y minus yp prime plus cy minus yp is the zero function. In particular, y minus yp is a solution to the homogeneous problem. So y minus yp is equal to, shall I call it a yh, where this is a homogeneous solution. Well, rearranging, this tells you y is equal to yp plus this homogeneous solution. So this argument is very, very similar to what we did when we were thinking about homogeneous and non-homogeneous linear systems. We saw that if I have a non-homogeneous linear system, if I give you a single solution to it, a general solution is a sum of that fixed choice of a particular solution and a homogeneous solution, so something which is a solution to ax is equal to 0. So it's exactly the same basic argument, actually. The mathematics is almost identical. So what's the conclusion? Well, let me make a few conclusions. The first is a general solution now to ay double prime plus cy prime plus cy is equal to f of t. Well, this is equal to what? It's going to be equal to a sum of my particular solution plus yh, where yh now is where all the generality is. This is a general solution to ay double prime plus by prime plus cy is equal to 0, the homogeneous problem. So this means if I find a particular solution and I find a general solution to the homogeneous problem, I'll find a general solution to this non-homogeneous differential equation. Let's also think about initial conditions. So remember what initial conditions are. I mean, they're giving a value of the function at a specific point t0 and a value of the derivative at a special point. So let's just make an observation that if I have yh at t0, yh prime, that's pretty badly written h, isn't it? It's yh prime at t0. So h here is a homogeneous solution. If this is equal to 0, 0, Well, what does this mean? Well, there's another homogeneous solution which also gives those initial conditions. In other words, the zero function. The zero function gives those initial conditions, and we know by the uniqueness of initial conditions for solutions to the homogeneous problem, this forces y of h has to be equal to the zero. So when I say zero here, I mean the zero function as usual. So if you're a homogeneous problem, and your initial conditions are 0, 0, you've got to be the zero function. So let's think what this means. So if, let's say, y of t naught, y prime of t naught, is equal to yp of t naught, yp prime of t naught, well, rearranging things, remember y is equal to yp plus yh, so this would force yh of t naught, yh prime of t naught, it's got to be equal to, well, 0, 0. So of course that implies by above yh is equal to 0. What does that guarantee? If yh is 0, that tells you y is equal to yp. In other words, if I give you initial conditions and I give two functions with the same initial conditions, which are solutions to the homogeneous or the non-homogeneous problem, they are automatically equal to each other by this result. So this is kind of an extension of the uniqueness of initial conditions for any given solution. So this is pretty nice. So this is a nice extension. So there's a bit of a problem now, a major issue that we run into, and it's the following. So to find a general solution now, all we've got to do is find a particular solution, really. We know how to find general solutions to homogeneous, we need to find particular solutions. So the problem is for a general f of t, there is no systematic or easy systematic way to find a particular solution. That's a major problem. So what am I going to do? Well, there's not much we can do short of restricting ft to be very specific. So that's what we're going to do. So this is called the method of undetermined coefficients. So let me state it. To find a particular solution to a y double prime plus by prime plus cy is equal to, well, a polynomial pmt times e to the kt, where this is a polynomial of degree m, could be constant, that just means it's degree 0. Well, the derivative of polynomials is polynomials, and the derivative of exponentials is exponential, so it makes sense we should look for a solution to this which is some sort of involves polynomials and exponentials. So it turns out you can always do it if we try the following. We're going to try yp is equal to, so bear with me a second, this is going to look a bit confusing to begin with. So let me write it out and then talk through. Okay, so what have I got here? Well, basically I've got a polynomial of degree m multiplied by e to the kt, and then at the front I've got this extra term, a t to the s. So I've got to tell you about this s. This s is kind of very important, and it depends on whether or not there are certain coincidences. So if k is not a 0 or a solution of auxiliary equation, in fact, let me write it like this. If ak squared plus bk plus c is not equal to 0, set S to be equal to 0. So if you're not a solution, you don't bother with the front term, it's just 1. If ak squared plus bk plus c is equal to 0, and it's not repeated, so it's not something like r minus 1 squared is equal to 0. So not repeated, set S to be equal to 1. If now ak squared plus bk plus c is equal to 0, repeated, set S to be equal to 2. Now let me tell you why I'm doing this. If you take, so let me just scrub the front a second. If you take that as your test case, and you take the second derivative of it, and you feed it into the left-hand side of the above equation. So you take this, you differentiate it a few times, and you work out what this is. When you go through the effort of doing that, you'll be able to simplify everything until eventually you have e to the kt multiplied by a polynomial. Now, what you need is a polynomial of degree m, because you need to get pm at the front. So you need this. And the problem is, if there are coincidences going on, like for example, if k is a root of the auxiliary equation, then what happens is the polynomial you get out on the left-hand side is going to be of degree too small. Now, if it's a non-repeated root, the degree will drop by 1. That's the reason you multiply by t, because that is allowing you to get up to degree m. If it's a repeated root, it would drop by 2, and that's the reason you multiply by t squared. Okay, so this is the reason we've got this ts. It's to allow us to deal with the case where k is potentially a root of the auxiliary equation, which would drop the degree of the polynomial once you feed it into the left-hand side. So this will always work. You will always be able to find a solution of this form. That trick is finding a0 to am that do the job. So that's half the problem. There's a bit more we can go for. So to find a particular solution, to the following now. So ay double prime plus by prime plus cy is equal to, well, one of two things now. Either pmt e to the kt cosine of lt, or pmt e to the kt sine of lt. So here I'm assuming L is not equal to 0, otherwise I'd be in the first case. If this is the case, we should try yp equal to ts, exactly the same as above basically. But now I've got sines and causes to include. So the confusing thing here is, in both cases, cos or sine, you need to have both causes and sines on the bottom, because the derivative of cos is sine, or negative sine, the derivative of sine is cos. So to get everything to balance out, you need two pieces, which is more unknown variables, unfortunately. So that's the general format. And again, the t to the s at the front is accommodating whether or not you have kind of a coincidence, whether or not e to the kt cos lt is a solution to the homogeneous, essentially. So if a of k plus il squared plus b of k plus il plus c is not equal to 0, set s to be equal to 0. So that's saying that k plus il is not a root of the characteristic polynomial. If now ak plus il squared plus bk plus il plus c is equal to 0, so it is a root, set s to be equal to 1. Now we don't have any repeated root here because it's a genuinely non-real root, so it can't be repeated because the other root has to be the complex conjugate. So there's no way you can be repeated. It's the same basic situation though. This one is worse because you've got two pieces to consider, not just one. And that's true for both the cos and the sine case. Okay. So, let's do this. So before I do some examples, I do want to introduce one more thing. Maybe I should say, what the basic aim here is the following. A remark. The aim is to find suitable. The aim is to find suitable A0 to AM, B0 to BM. That's what we want to do. We're trying to find appropriate constants, okay? Just A0 to AM in the first case, B0 to BM as well in the second case. So what we do is we take these kind of general formats, we work out the first and second derivatives, we calculate the left-hand side, and then we need to gather terms together to get them into the format of the right-hand side. And we're going to have a bunch of coefficients, we're going to have a bunch of polynomials with a bunch of coefficients in unknowns, and we're going to have to somehow make choices of A0 to AM, B0 to AM to match everything up. That will always turn into a piece of linear algebra. So this will always lead to solving a linear system. It will always lead to solving a linear system. So, before I give some examples, in fact what I'm going to do is I'm going to finish this video just with the abstract theory, and then in a second video I'm going to go through a few examples to illustrate this. But to finish off the entire technique, I want to say something about how I can extend it a little bit further. So by a little bit further, what I mean is the following. Can I deal with things like sums and differences? So the superposition principle allows us to extend this technique a small amount. So if ay1 double prime plus by1 prime plus cy1 is equal to some function f1t, and ay2 double prime plus by2 prime plus cy2 is equal to some f2t, well, these two things guarantee that y1 plus y2 is a solution to the differential equation ay double prime plus by prime plus cy is equal to, well, f1t plus f2t. So that means the following. If I have a non-homogeneous linear differential equation and I take the right-hand side, the f, if I break it into the sum of things of the form polynomials times exponentials times sine and cos, I can apply the method of undetermined coefficients to each of those and then sum up all of my particular solutions. So let me do an overview of the entire strategy now. So, what do we do first if we're trying to solve these? So by solve, I mean a general solution, or maybe try to find a solution which satisfies particular initial conditions. The first thing you should always do is find the general solution to the homogeneous using the auxiliary polynomial. Once I solve that, I can basically immediately read off a general solution to the homogeneous problem. Second, well, I need to find particular solutions. Using the superposition principle, what I should do is the following. I should break up, assuming this is possible, there are plenty of examples where we just have no way of doing this. We could break up f of t into the sum of functions of the form, well, pmt, e to the kt, pmt, e to the kt cos lt, or I suppose finally pmt e to the kt sine lt. So I'm breaking them up into the sum of these things because then I'm going to apply the superposition principle. Find particular solutions for each piece separately. It's important. You want to take each of these pieces and completely separately find particular solutions. So is that piece? It should be piece. For each piece separately, using the method of separation, so using the method of undetermined coefficients. So do those completely separately. The reason you want to do them completely separately is, remember that t to the s business? The t to the s business is a problem because some pieces may have s is equal to 0, some pieces may have s is equal to 1, some pieces may have s is equal to 2. You can't have one s for all of them, so you can't do them all together. So you have to do them all separately. So once we've got all of this, we'll have particular solutions to each piece. The sum will be a particular solution to my original guy by the superposition principle. Then I just add it to the general homogeneous solution. So sum, the general homogeneous solution, and all my particular solutions. To get a general solution to a y double prime plus by prime plus cy is equal to f of t. That's the basic strategy. One little extra piece, if you have an initial condition, so given initial conditions, what we do is calculate, well, you take your general solution from 4, calculate y of t naught, y prime of t naught, you set those equal to your initial conditions and you solve. Calculate this. So maybe I should just actually be quite precise about this. Given initial conditions, so I'll say I don't know. I'll say alpha beta for the moment. So calculate these two. Set, what will it be? Yt naught. Actually, I'll just do two of them side by side. Y of t naught equal to alpha. Y prime of t naught equal to beta. And what? Well, remember, these are your general solutions from 4, so the only unknowns are C1 and C2 in the homogeneous piece. So you're going to get two equations and two unknowns, C1 and C2. They'll both be linear, very straightforward. You just solve using basic 2x2 matrix theory. So, and solve for C1 and C2. So that's the method. That's the method. That will work every single time. The problem with this method is it's the undetermined coefficients piece, in the sense that it's incredibly time consuming to go through this. It can be very difficult to explicitly work things out because you end up with so many equations and so many unknowns. So in the next video, an examples video, I'll go through a bunch of examples to illustrate